Thank you. Good morning, everyone. Thank you a lot for joining in. I'm really looking forward to all these talks during these 2 days, and now I will do my part of the job. So I will also talk about generalized Nash equilibrium problems, and in particular, talking about some works we did with Monica. And we were mainly interested in finding numerical methods to compute the Nash equilibriums. And what I will talk about today is not, I will not present like a new, very fancy method. What I want to share with you is more an idea and more motivations to study a family of dynamical systems that might be very helpful in this context. So that's a very mysterious beginning, but so my talk will be in 2 parts. I will first introduce once again the GNEP and maybe motivate a bit more some of the classical assumptions. And then second part of the talk will be about this non-smooth dynamics that I want to talk about. Perfect. So very basic beginning. Let's say we are interested in a nonlinear optimization problem, and which means I have a variable x that will live in some nice space. So let's say Rn or an Hilbert space. And you have a cost function, a set of constraints, and you want to minimize this function f over c. And during all my talk, I will try to keep C as general as possible, but you can think about some set described by inequalities. And my usual aim is to get numerical methods for this, and which are mainly based on using derivatives for very practical reasons, because I believe it's a good trade-off between efficiency and theoretical guarantees. So in general, we are interested in local solutions or stationary points unless the whole problem is convex. Okay, so that's very classical. And now I'm suggesting we look at a problem where we have 2 optimization problems at the same time. And these 2 optimizers, we call them players, and each of them has a strategy, and each of them want to minimize an optimization problem. And the funny thing is that the cost function and the constraint set of each player depends on other strategy. Okay, so that's what we call the non-cooperative 2 players game, because we have 2 players here. And you can, since you can do it for 2 players, you can easily generalize to an arbitrary large but finite number of players. So we are really living on a product space. Okay. And what is very important here is that the constraint set is not just a classical set here, it's a point to set mapping, right? Because for instance, C1 of x2, for each value of x2, it's something different, and it might be even empty sometimes. Okay. So this family of simultaneous optimization problem leads us to consider the generalized Nash equilibrium problem, which is really a solution concept for this kind of games. And our definition is very standard. Then X star will be a GNE if X star new is a solution of the newest optimization problem. Okay. So X new is the strategy of player new, and X minus new is the vector of all the other strategy. Okay, and maybe to fix a bit, to fix it a bit in your mind, here is a small example that is very standard. And also, I want to point out, if you do the computations, so you'll have to trust me on this. So the solution set is a closed line. So most of the time, there will never be a unique solution to this problem, but a whole set of points. Okay. And this problem is very specific because you can see both players have the same constraint set, and this is what we will call a GNSC, a generalized Nash game with shared constraints. Okay, so it means that there exists some set K that both players are sharing. Here. Perfect. So we had already a couple of talks on GNEP, so maybe it's no need to motivate further. Also, I want to talk about some classical assumptions we will make. So usually we will assume that the cost function is convex with respect to the X new strategy, so the variable we are optimizing. And we will also assume that f nu is C1 because I want to use gradients. And two more assumptions on the point-to-set mapping, on the constraint mapping. So I have some compact convex set S nu, and my point-to-set mapping maps S nu to a subset of S nu, and it has non-empty compact and convex values. Okay. So actually, the domain of C nu is not the whole space, but some compact part of the set, or strongly compacted than if you are in a Hilbert space. And what do we get from these assumptions that are very classical? First thing is that each optimization problem is convex if you fix x minus nu, because C nu of x minus nu is always convex then. And the objective function is convex. Another consequence of these three assumptions is that the point-to-set mapping C as so the product of the C nu as a fixed point. So that follows from the Kakutani's fixed point theorem, and more or less a direct consequence of that is that there exists a generalized Nash equilibrium. So that's very standard assumptions. Perfect. And also thanks to these assumptions, we have some very handy reformulations of the problem. And one of interest is reformulating this problem as a quasi-variational inequality. So let's say you replace each optimization problem by its optimality condition. So you get for each problem a variational inequality, which we call quasi, because you see that the C nu set depends on the strategy as well. And if I'm concatenating all these inequalities for the n players, I got what we call the quasi-variational inequality. Okay. So this is equivalent to the GNEP problem. To finding the GNEP, that's a bit old reformulation, I believe. And I will rephrase this quasi-variational inequality in a different way. So if you recall, what is the normal cone to a convex set? So here my convex set is C of x. So the normal cone of C of x to x is this set. Then using this, I can rewrite the QVI as an inclusion. That's the minus the concatenation of the gradients belong to the normal cone of C of x at x. So my C of x is really the product set of the C nu. Okay, so the product of all the constraint set. Great. Okay, so further remarks, more remarks on the GNEP. I believe it's always interesting to understand a problem to see what is underneath. So let's talk about some special cases. The first very classical one is when C nu, when the constraint set actually does not depend on other strategy, then you have the original Nash game. So that's why I'm adding a generalized all the time. And another particular case of the GNE, if you assume that all the objective functions are constant, then what you are doing is really trying to find a fixed point of a point-to-set mapping, okay? And it's just to find a fixed point because that's not so easy as a problem in general. Okay. And to say further about this, to say more about this, so really one of the difficult things here is to find a fixed point of this point-to-set mapping. And just as an example, what would happen if we want to build the classical fixed point iteration? Okay, so if I'm computing a sequence xk, such that xk plus 1 is just the projection of xk over c of xk. Okay, so if I'm doing something like this, we can have a couple of difficulties. First, we want to be able to project, so we need some convexity on c of xk. So that explains why we need convex values. Also, you can observe that if c of xk is empty at some point, then we are stuck. And of course, because the set is moving all the time, we might actually never converge. I didn't give any illustration here, but you can find some very nice one on Wikipedia, for instance. And so, especially for this problem, we have one strong assumption, which is to suppose some contractive properties of C. And one would be the following one. Let's say we have some constant L1, which will be between 0 and 1, such that the distance function will be a contraction. Okay, so really it's respect with how the set is moving here. Okay, the U and V is for the C and U, C and V. Okay, so under this type of assumption plus the convexity plus our previous assumptions, then this fixed point iteration will converge to a fixed point. Perfect. Okay, so that's a very general presentation of the GNEP and my framework and main assumptions. Now what I want to talk about is more about some non-smooth dynamics which is connected with it. So remember we had this QVI reformulation, which was here. And what I am suggesting here is, let's say we have some differential system that starts from one initial point and will reach a Nash equilibrium when it reaches a stable state. Okay, so I'm considering this dynamical system, this dynamic differential inclusion. Okay, where you can really see that if x dot is equal to 0, so when it reaches a stable state, then we have GNE then. Okay. Perfect. And so one tricky thing here, it's not like classical differential equations, because it's in inclusion and because of this cone, because of the normal cone, the derivative might not exist at some point. So the solution will not be, the solution of this differential inclusion will not be C1, okay? So it will be absolutely continuous or Lipschitz continuous, depending on the case. And also because of the normal cone, there is one strong observation is that at all time, x of t will belong to the set C of x of t, okay? So that's really a differential system that lives in the set of fixed point of C, okay? So some would like, or some might find useful to have a reformulation of this differential inclusion as a differential equation. And you can do it in some sense. So let's say Tk of V is the tangent cone to K at V, okay? Then this differential inclusion can be reformulated in some sense as a projected dynamical system, where now the dynamics is equal to the projection of the gradients over the tangent cone, okay? And so a solution of 2 will be a solution of 1, and the slow solution, so a specific type of solution of 1 will be solution of 2, okay? So there is some sort of equivalence between the two formulations, okay? And even so as I said before, even so that's a differential equation now. The right-hand side will not be Lipschitz continuous, so the solution will not be C1. Great, so now we have this family of dynamical system, and maybe I should motivate this a bit further. So apart from the fact that that's a beautiful equation, mainly I have two strong motivations to study this. The first one is very natural, actually. So studying the solution X might have some meanings depending on the application. And the obvious one is in evolutionary game theory, where people are not just interested in the equilibria, but also in the evolution of the population over time. And so this type of equation would be a generalization of what Sandholm and co-authors, for instance, call the projection dynamics for evolutionary game theory, which would maybe would means that the population are doing revisions driven by insecurity. So I don't want to talk a lot about this, but so the path in itself might have some meanings. And another motivation, which is really the one I want to share with you, is from the point of view of a numerical method. So if we assume that there exists a solution to this dynamics, and we know that the stable states are asymptotically stable, then really a solution of this differential inclusion starting from the initial point x0 goes to the solution. So it's building a path from an initial point to the solution of the GNE, which is exactly what numerical methods are trying to do. So more or less, any approach that will try to follow this path, the solution of the differential inclusion, will be a numerical method. Okay, and this method, if it follows the path close enough, it will converge to a GNE. And then you can translate the language from differential inclusion to numerical methods. If you have asymptotic stability, as I said before, it will give you a global convergence in the sense that it will converge from any initial point. And then if you have local stability, it's going to be a locally convergent method. And you can even say additional things, like if you have exponential stability, it's going to give you a rate of convergence, for instance. Okay, so that's a very, I believe, interesting point of view, which is going to the main idea of what is a numerical method. And that's completely different from the initial motivation to study these systems. I believe the first one would go back to Moreau in the 70s, introducing what we call, at least in France, the Moreau sweeping process, or just the sweeping process, which is just this differential inclusion, where now it's just a C of t and not C of x of t. So if you see on my figure on the right, you have this disk that is moving all the time. So that's my C of t. And you are trying to find a solution x such that x belongs to C of t all the time. So C is moving and x is following. Okay. Original application was from plasticity theory, contact problems in physics. So you see it's quite far from numerical methods for GNE. And since we have a t here, that leads us to another observation, that actually, instead of having just a C of x of t here, I could add, since I'm only interested in the stable states, I can add a regularization parameter and consider now a C of x and t. And now t would not be the time from Moreau's application, but would be some regularization parameter, for instance. Okay, so if your set C is too small and you want to regularize it for some reasons, then T would be this parameter. Okay, so let's say T is in the interval T0 Tf, and then regularization would need some convergence property like the distance function, so which is regularized. Now you see the C of T and U would in some sense converge to the distance to C of U. Okay. So here that's a classical distance, but if you have the similar property on the host of distance, for instance, it would work. Okay, so we can extend further this interesting dynamics like that, adding a regularization parameter, for instance, in the set C, or also in the perturbation in the gradients. Okay, perfect. So what would be the strategy now? So that's a three-step approach. Yeah. So that's really a three-step approach. First, you want to prove that there exists a path. So find some framework where it exists. Then prove that this path will reach a stable state. And then the only thing we have to do is to compute and approximate this path all the way to the stable state, which will be a GNE. Okay. If you are very lazy, as I am sometimes, you can just try to track the path, and even if it doesn't exist, like as a heuristic. And also I want to point out that studying theory might be painful sometimes, but it's very useful because most of these existence proofs are constructive actually. So they are based on methodology. And to give you a small idea of what type of existence result we can have, here is a very general one. So if you remember from the beginning, I have this contraction assumption, which we recognized here again, that the distance must satisfy some contraction property with respect to u and v, and just a Lipschitz property with respect to the time, or the regularization parameter, depending on your point of view. Then assuming that your gradients are not going crazy, you will have a Lipschitz solution of the differential inclusion. So if some of you are quite surprised that it's Lipschitz solution and not absolutely continuous, it's because we are living in a strongly compact set. So the solution will be Lipschitz here. Perfect. And really what I want to stress out, so this result is very classical, and you can find different versions of them in the very recent literature. And what I believe is a very, very strong assumption is this contraction property, which is not satisfied by a lot of games we have. And really, you can say some things if you have some knowledge of what is the fixed point of this C. So I gave a small example of shared constraints earlier. Also, Lacra gave some applications of this. So if you have a shared constraint type problem, then you can say some more things. You can skip this contraction property. Also, if the set is described by inequalities that satisfy constraint qualification, also you can be a bit more specific with this. No. Okay. And just to point out that it's very ongoing research for the general case. So from the Morrow sweeping process literatures, you'll see from this list that a bunch of results are from the past 2 years. Maybe we don't see the last one, Thibault and Salas from 2020, like very recent papers. And we are still very much stuck with this contraction property. So at least for our general case. So really a lot of ongoing research here needs to be addressed. And so I told you, first point is to prove existence. I'm to save some time, I'm skipping the stability here. Also, I'm maybe I have just 5 minutes. So I want to give like 2 very simple examples among a lot of others. 2 simple examples of numerical methods you can get from that. The first one would be to do a Morrow-Yoshida regularization, meaning you approximate your differential inclusion with a nice differential equation. Okay, so you are computing this solution x lambda, which is going to be a smooth solution, C1 of this differential equation. And then if you push lambda to 0, you will recover the solution of the differential inclusion. Okay, so you can give this to one of your favorites ODE solver, and it will give you something. And another approach is what sometimes we call the catching up algorithm, which is this idea of projecting of the set again and again and again. And so here I'm giving one scheme. And so everything is hidden in the mu n. And when you push n to, so the discretization step to 0, so my capital N to infinity, then you will recover the differential inclusion as well. And so you can maybe recognize the projection methods Anna Maria just described. Okay, so that's two among a lot of methods. And maybe, yeah, I will just skip to the conclusion. So I've been very quick, but I wanted to share with you this idea and revisit this idea that a numerical method is a path starting from an initial point and leading to the solution of the QVI or GNEP. And because the path is continuous and have some properties, we can follow it kind of closely. And if you think about it, this resembles a lot what we are saying about interior point methods and all its variants, which are all of them just following the central path, actually. Okay, so that's revisiting the same idea. And there are a couple of main benefits of this. First of all, it allows a uniform analysis of a lot of numerical methods. So I told you the catching up algorithm resembles a lot projection algorithms for QVIs, but also if you think about it, some Gauss-Seidel or Jacobi decomposition methods that are used for the GNEP exactly belong to this framework, okay? And also from the existence literature, you can study this method in a generic framework in infinite dimensional space. Here I assume that the objective function was C1, but you can do something non-smooth as well and use, as I presented, a generic constraint set. Okay, and another benefit, which I believe is very interesting, is that we not only compute the variational equilibria, but any GNE that will have some stability properties. Okay, and as I point out, it's a lot of ongoing research from the theoretical side, and hopefully it will manage to solve most of the open problems soon. So maybe I'll skip that. Just to say that part of what I've said is in this paper we published with Monica that was published very recently. And let me thank you for your attention. And maybe you have some question, maybe you want to enjoy the break.
Thank you, Tangi. Yes, everyone, please ask some questions. We can spare a couple of minutes, and then of course is a break, so feel free to socialize here or just take a break. So you can use the chat or you can use your microphone if you have any questions for Tangi. Okay, I think we are good to, oh, how long is the break? Yes, the break is half an hour. So we are convening here.
Monica, I typed in a question, but it didn't seem to transmit.
Oh, yes, go ahead.
So I don't know why it didn't transmit. I said, is there any hope of a LaSalle or a Liopuno function for carrying out a stability analysis?
Yeah, completely agree. I completely skipped this part here. But yes. And also a lot can be said because it's from a game's point of view. For instance, we have some assumptions that may come from the game application. Like I'm thinking about if you have a potential game where all the solutions will be minimum of some magical functions, and that's gonna help a lot to prove stability as well.